The valence shell electron pair repulsion theory, which is used to determine the three-dimensional shapes of molecules, is a very important piece of subject matter you encounter rather early into your A-level chemistry journey. Using just the number of outer electron pair regions surrounding the central atom, we are able to determine the bond angle between three atoms either in a small molecule or at various points on a larger, perhaps organic structure. Among the various shapes we encounter at A-level, there is one particular combination of electron pair regions surrounding the central atom which is more popular than others. In this video, I'll be looking at the differences between the three different three-dimensional shapes that arise when we have four electron pair regions surrounding the central atom. Our first shape is the staple of the three, and a very common shape seen throughout organic chemistry. It occurs when the four electron pair regions surrounding the central atom are all bond pairs of electrons. This is seen here surrounding the carbon atom in a molecule of methane. The four electron bond pairs all repel each other equally, putting a bond angle of 109.5 degrees between any atoms surrounding the carbon. The shape is called tetrahedral, and when drawing it three-dimensionally, we need to represent that two of the four bonds are not in the same plane as the others. To draw a bond coming out towards us, we use a triangular wedge block, and to show one going away, we need to use the same shape but using hashed lines. At a first glance, our next shape, once it's been drawn, looks really similar, but with the new presence of a lone pair on the central atom, we're going to have to adjust the bond angle. The example I'm using is AsH3. The arsenic is in group 5 like nitrogen, and so therefore has 5 outer electrons. The formula tells me I need to have 3 of these 5 electrons in bonds with hydrogen, and that leaves 2 electrons left over surrounding the central atom as a lone pair. Lone pairs repel more than bond pairs, therefore we can state that lone pair to bond pair repulsion is going to be greater than bond pair to bond pair repulsion. This reduces the bond angle as the atoms surrounding the arsenic are pushed closer together. The new angle is 107 degrees and the shape is pyramidal. The three-dimensional diagram looks just like the base of tetrahedral, but the top site is used instead this time for a lone pair. Our final shape using 4 electron pair regions is called nonlinear. The central atom is tellurium this time, which is in group 6 of the periodic table, giving it 6 outer electrons. 2 of these 6 are used in covalent bonds, according to the formula, leaving 4 outer electrons which form 2 lone pairs. So this time, our 4 electron pair regions are a combination of 2 bond pairs and 2 lone pairs. Remembering that lone pairs repel more than bond pairs, our shape and bond angle need to reflect the fact that lone pair to lone pair repulsion will be greater than lone pair to bond pair repulsion, and that this is then greater than bond pair to bond pair repulsion. As a result, the atoms surrounding the tellurium are pushed closer together than those surrounding the arsenic in the previous example. The angle is reduced to 104.5 degrees. So that's it for this tutorial. Hopefully this gives you some background onto the 3 different types of shape using 4 electron pair regions around a central atom. If you found this video helpful, then I'd really appreciate it if you could give it a like before you go and consider subscribing to stay updated. Until next time, happy revising.